Hi, let's move on to the second part of the advanced matrix multiplication lecture. In the last lecture, we have learned that the matrix multiplication is composed of three loops, one for the I, one for the J, and one for the K. And we're free to pipeline or unroll any of these loops, but in terms of performance and the internal memory consumption, it is usually the best if you can pipeline the J loop and unroll the K loop, right? It'll give you decent performance because you have adequate parallelism of M mag operations per cycle, and you're not going to consume too much internal memory because you only need to partition A and B by M, and not fully partition any of the memories. In the code, we can put the pipeline progma up here, and we can also put the array partition progma to tell the compiler to partition the memories. And we could also write down array reshape progma if you want to further simplify the internal memory structure and the control logic. And we also learned last time that all the elements in the matrix will be reused to produce the result. For example, A11 will be multiplied with the B11 to produce a part of AB11. And A11 will also be multiplied with the B12 to produce a part of AB12. So A11 can be reused up to P times if it has been stored in the internal memory. But if we cannot fit the matrix in the internal memory, we will have to fetch each element from the DRAM every time we need it. So the challenge was to how to exploit this data reuse opportunity, even if the entire matrices cannot fit inside the FPGA's internal memory. And that is the question we'll be answering today. To solve this problem, we'll use something called a blocked matrix multiplication. Today's learning objective is to be able to explain the advantage of the blocked matrix multiplication, and we'll learn how to optimize our blocked matrix multiplication implementation. So the main idea of block matrix multiplication is to partition a matrix into smaller blocks and process only a block of matrix at a time. For example, let's divide a matrix into 16 submatrices. This is not an element, this is just a part of a matrix with several elements on its own. Okay, so we're going to multiply this submatrix A11 with this submatrix B11 and add that to the multiplication of submatrix A12 and B21 and so on. We're going to do that, keep doing that for all these four submatrices and add up to the submatrix AB11. Okay, and we're going to do this operation for all the submatrices in AB. All right, so that's the what block matrix multiplication is doing. And now if you think about how many submatrices we need to store in the FPGA internal memory at the same time, we need to keep storing AB11 because it'll be accessed continuously when doing this computation. But for A and B, we only need to store one submatrix from A and one submatrix from B, because after multiplying A11 and B11, they are no longer needed. So we can just throw them away and fetch A12 and B21, right? And you can throw them away and fetch A13 and B31 and so on. Okay, so that's why we only need to store 3 submatrices in the internal memory at a time, one from A, one from B, and one from AB. So the blocked matrix multiplication can really help you reduce the internal memory consumption. Okay. By the way, if you have a large internal memory, you can go with the large block size. If you have a small internal memory, you can just go with the small block size. Okay. You can still exploit data reuse with the blocked matrix multiplication, although not as much when you store all the matrices in the DRAM. We'll try to quantify that by measuring the DRAM transfer size and the internal memory consumption. We're now going to see the details of the blocked matrix multiplication and discuss the loop ordering, DRAM transfer size, and the internal memory consumption. Suppose that we're multiplying matrices of size n by n, and we're partitioning them into blocks of m by m. So this is the matrix size, and this is the block size. We first need to decide on the order of block computation. There are several ways of doing this, but for convenience, let's just choose the most intuitive one, the IJK loop. So once again, this is a block, not an element, and we're going to multiply this block with this block and add up to AB11, multiply this block and add up to AB11, and so on. And we can express this in triple loops, I, J, K block loops, okay? And this loop ordering means that we're going to compute AB11 first, and then AB12, AB13, AB14, AB21, AB22, and so on. And that's because JB, this one is the inner loop, and IB, this one is the outer loop. And in order to compute AB11, we're going to traverse in KB loop, this one, which is this thing, okay? So which is fetching a block of A and fetching a block of B. So A11, B11, multiply and add, A12, B21, multiply, add, and so on. Okay, so that's the role of the KB loop, this one. All right. Next, if you think about how many iterations we need for the block loops, assuming the matrix size is n and the block size is m, we need to iterate for n over m times. Okay. So if we adopt such ordering among the blocks, we can count how much data should be transferred from DRAM when we use blocked matrix multiplication. Let's start with the AB. There are n over m times n over m of a small AB block, right? Each small AB block was of a size m squared. So the data transfer size of AB is going to be m times n over m times n over m, which comes down to n squared. And all of them are right, no read. Next, we count the DRAM transfer size for A. For each AB block, we need to fetch a small block of A n over m times, right? So to compute AB11, we need to multiply this with this one with this one. So in terms of A, we need to fetch n over m times just to compute AB11. And since the AB11 needs to be computed n over m times, right? And each A block is of size m squared, right? So the transfer size for A is going to be m times n over m, this number, times n over m, which is this number. Okay, so if you just multiply everything, it's going to be n cubed over m. And you can easily check that the transfer size is the same for B as well, right? And both of them are going to be all read transfers. So if you sum up these three terms, n cubed over m is typically much larger than the n squared when the n is much bigger than m. So these terms combined is going to be approximately 2 times n cubed over m. And we know that the total transfer size when it is not blocked is going to be 2 times n cubed. So the DRAM transfer size was reduced by a factor of m. Okay. But we should ask ourselves at what cost? Well, we are consuming internal memory, right? But how many? The answer to that actually depends on the loop ordering within a block. So what we saw until now was the block loops, and we also have to figure out the loop ordering inside the block. Let's see how it's done in the next slide. So now we are inside the blocks, and the 3 block loops we saw before are somewhere here. And inside the blocks, we're going to do the element-wise computation. As before, we're going to have 3 loops, I, j, and k, and the size of the blocks is m by m by m, and that's what you see for the length of each loop. The computation pattern is same as before. For each I and j element of AB, we're going to accumulate on the k loop. Okay. Now, this code assumes that the loop order inside a block is I, and then j, and then k. And let me ask you a question. Can we interchange the I and the j loops? By interchange, I mean, can we swap the location of I and j loops and still get the correct result for the AB block? The answer is yes. If we change the location of I and j loop, the only difference is that we're going to get the AB block in a different order of I and j. There's no difference in the final value, right? Okay, so the next question, can we interchange j and k loops and still get the correct result? Well, if we interchange j and k, we are no longer going to initialize the value of AB temp to 0 before the k loop, right? And that's why no, we cannot interchange j and k loops, but if we had a separate loop that properly initializes everything in the j loop somewhere here, then it would be okay to swap the location of j and k loops. Let's see how it's done in the next slide. Here's the code. We did change the ordering of the k and j loops, and rather than having a single element initialized to 0 here, we're now initializing the whole j loop up here, right? Then all the elements in the AB block will be initialized before the accumulation, and we're going to get the same result as the previous code. Make sense? So the lesson here is that we can pretty much change the loop ordering in any way we want. We just need to modify the code for the AB block initialization before each ordering, right? So I hope you are persuaded by this statement by now. Now the natural question is that which loop ordering should we use? That is, if we have the choice, what ordering is going to give us the best trade-off between the performance and the resource consumption? Well, there is no single right answer, but let me explain some factors that you should consider. So the first thing you should consider when deciding on the loop ordering is the data reuse and the internal memory usage. Let's pick a specific element to figure this out, A11. So A11 can be reused across loop J. That is, it'll be multiplied with the B11 to produce a part of AB11, and the A11 will also be multiplied with the B12 to produce a part of AB12, and so on. Now let's think about B11. B11 can be reused across loop I, meaning that it'll be multiplied with the A11 to produce a part of AB11. B11 will also be multiplied with the A21 to produce a part of AB21, and so on. So this reuse opportunity exists regardless of the code you use, but the cost of exploiting this data reuse will be different depending on the loop ordering. For example, let's suppose that we use a loop order of K, I, J. That is, the outermost loop is K, and then comes the I loop, and then the innermost loop is the J loop. We already agreed that we can reorder the loops freely as long as we do the initialization properly. So from the viewpoint of accessing A11, we're going to order the loops K, I, J. You see that we keep accessing the same A11 in the J loop, the innermost loop. Or here, let's look at it here. It's K, I, J. Remember that we use the same A11 to multiply with the B11, B12, B13, and B14, right? So if the J is the innermost loop, we reuse A11 in the immediate next iteration. Then we say that the reuse distance is 1, meaning that the A11 will be reused 1 iteration later. Let's look at it from the viewpoint of a B11. Again, the loop order is K, I, J. So after accessing B11, when is it reused? Is it the next iteration? No, the loop order is K, I, J. So B12 is going to be accessed in the next iteration. B11 will be accessed 1, 2, 3, 4, so m iterations later. Make sense? So let's look at it in the left picture. So it's a K, I, J. So B11 will be multiplied with the A11, and the B12 will be multiplied with the A11, right? And when is B11 gets accessed? 1, 2, 3, 4. B11 will be accessed m iteration later to be multiplied with the A21. Okay, so if the loop order is Kij, B11 has a reuse distance of m. Okay, so the reuse distance is just a fancy way of saying how often the data is accessed again. Let's move on to the next example when the loop order is Kji. Okay, so Kji. So A11 is first going to be multiplied with the B11, and since it's a K, ji, the A21 is going to be multiplied with the B11, and then the A31 and the A41, right? So the reuse distance for A11 is going to be 1, 2, 3, 4. So m iterations later, because it'll be access m iteration later to be multiplied with the B12. Okay, so the reuse distance for A11 when the loop order is KJI is going to be m. Okay, let's look at it from the B11. The B11, the loop order is KJI. So B11 is going to be multiplied with the A11, and in the next I iteration, it'll be multiplied with the A21, and so on. Okay, so since the B11 gets reused in the immediate next iteration, the B11 for the loop order of KJI, the reused distance is going to be 1. So from these exercises, you can see that depending on the loop order, the reuse distance is going to change. And why does it even matter? It matters because the reuse distance is related to the internal memory usage. Let's look at this in details in the next slide. Let's think about the relationship between the loop ordering and the internal memory usage. Again, we assume that the loop ordering is K, I, J. So for A, we only need a single register because it is going to be reused in the next iteration. But for B, we need a memory of size M because the B's reuse distance is M. So the reuse distance of M actually means that we need to hold the data for M iterations. But it also suggests that in the meantime, other data of B are going to be accessed. So we need to keep storing those other data, and that's why we need an internal memory of size M for B. Make sense? So what I'm trying to say here is that the internal memory usage is closely related to the reuse distance. I'm listing lots of different loop ordering here. We already saw that for KJI, the reuse distance for A is M, and the reuse distance for B is 1. Right, so this means that we need an internal memory of size M for A and 1 for B. So Kij and Kji has a similar memory usage. It's just that the size of A and B are swapped, right? And let's move on to the next loop ordering, IJK, which was the original loop ordering. Please check on your own that the reuse distance for A is M and the reuse distance for B is M squared. It consumes larger internal memory compared to these two orderings, and you probably want to avoid this one and take one of these two. All right, so let's summarize the internal memory usage, assuming that the loop ordering is Kij. We need a single register for A and a memory of size M for B. This means that we are storing a line of B, right? For AB, we need to store a block M squared because of the loop ordering among the blocks. Remember that we decided to keep storing AB in the internal memory while fetching just one block of A and one block of B at a time, right? So these loop orderings we just discussed are within a block, and as long as we decide to take the IJK among the blocks, we still need a block for AB. Okay. So now we know what to expect for the internal memory usage. So let's make a comparison here and summarize. So compared to the non-blocked version of matrix multiplication, we can save on the DRAM transfer with the blocked matrix multiplication by a factor of m. But to achieve this, we have to consume the internal memory to store the data. The exact number depends on the loop ordering inside the block, but it's approximately m squared. So there exists a trade-off between the internal memory usage and the DRAM transfer, and this is typically a good trade-off because if we go with the non-blocked version, like in the last lecture, the DRAM transfer overwhelms the available resource, and the performance is going to be awful. So if we reduce it with the blocks matrix multiplication, we'll almost always improve the performance. And also keep in mind that depending on the internal memory you have on the FPGA, you could move the trade-off point by adjusting m. That's the size of the block. Okay. Just one more thing before we see the actual HLS code. The second decision factor you should consider before deciding on the loop ordering is the DRAM access pattern. The data is stored in row major in most computer systems. Row major means that in the DRAM, A11 is stored next to A12, but not A21. Okay, so this way would be the column major, and the data is usually stored this way. Since data is stored in row major, DRAM effective bandwidth is improved if the innermost loop accesses the same row. So DRAM goes into something called the burst access mode that maximizes the effective bandwidth, but this is possible only when accessing a consecutive data in the same row. So when deciding on the loop order, we want to choose an order that allows you to access the data in the same row. Okay. So for example, let's say that the loop order is K, I, J. When accessing the matrix B, you're going in a J loop first, okay, and the next I iteration, which is just the same row, okay, and you keep doing this until you go to the next K, right? Kij. So we're done with the Ji loop, and then you're going to the next K loop, which is this one. That's the second row. Okay. So and over again, and then the next row and the next row. So every access in matrix B is going in the row direction, and this is good for high bandwidth. But for A, we're going to access J, same one, and then we're going to the next I, which is this direction, right? And then we go to the next K, which is the next column, and the next column. So all the accesses are going to be in the column direction, and this is bad for DRAM bandwidth. Okay. Let's go on to C. So for C, we're going to access in J direction first, and the next I, which is all rows, and then we're going to the next K, which is the same thing. Okay, same pattern again. So for C, it's also good for high bandwidth. So for each loop ordering, you can do a similar analysis for each different matrix and figure out whether the DRAM access pattern is good for high bandwidth. There are some loop ordering like a KJI, which turns out that the DRAM access pattern is bad for all the matrices. Okay. And for like IJK, A and C are going to be good. It's going to be bad for the matrix B. Okay. You can verify if this is true on your own. Um, so the what I'm trying to say is that the DRAM access pattern is another thing you should consider when you decide the loop ordering inside the block. Okay. And actually, let me give you some spoilers ahead. We are going to choose the loop order Kij. We already saw that this order has a problem in accessing matrix A, right? But we'll learn how to fix this problem in the next lecture, right? And by the way, the whole analysis that we have seen so far is not really FPGA or HLS specific, that the same analysis can be applied on CPU or GPUs as well. You know, just letting you know, okay? So, and let's get started with the FPGA and the HLS optimization in the next slide. We're now going to make a program for the blocked matrix multiplication. Let's start by creating a Vitis project. You can follow the directions given in the previous lecture, the Vitis and the Vitis HLS flows. This is just a summary, so you can first copy the project from the hello world and modify the files one by one. For the host file, you can create a memory object for the A, B, and AB, and set the corresponding kernel arguments, make the PCI transfer, and launch the kernel. Remember, right? And the for the make file, you can just change the directory name and the kernel name to match this matrix location. Then you can make the kernel code. Let's set the type to the short type and the block size to 256. And you probably remember that you have to put an external C around the top kernel function in a Vitis project. And for the argument, if the matrix size can change, it's better to put them as a pointer rather than fixed size arrays. And the matrix size n is made configurable as a scalar argument. We're going to assign the AXI interface to these arguments. And for the bundle, let's assign a different bundle for A and B because they are going to be accessed at the same time. It doesn't matter too much for AB because AB writes happen far less times compared to A and B reads. So I just assigned the same bundle as B. And we need some internal memory for the blocked matrix multiplication. Let's assume that we're taking the Kij loop order. And if you remember a few slides back, we need a block storage for AB, a line for B, and just a single register for A, which you'll see in the next slide. Then we need the block loops, these three loops. I'm going to skip some of the initialization code because it's pretty obvious. And within this block, we are going to have the Kij loops. The J loop is up here just to fetch some data for B, but the main computation are these ones, Kij. And since all the arguments are now in a pointer, not a 2D array, that the data copy routine, this one for B, might seem a little bit complicated, but it's really just a 1D array addressing after blocking. So N was the matrix size, and M is the block size, and J is the index within a block, and JB is the block index. So you can just see that this thing is just a bracket J, right? The column with the new index, and this thing is just a bracket K, the row with the new index. You just have to multiply by n the matrix size. Make sense? And this is also just a 1D array indexing for A, I, K. Okay. And in the main computation, we're multiplying one element of A with the whole line of B, okay, to produce a line of AB in the J loop, the column. And if you want to produce a different row, you're going to do that with the I loop, right? And we should do these things for all the K loops as well. Then we're going to be done with the computation for one block of AB, and you should write the result to the DRAM here, which I'll omit the details. And then you can move on to the next block with these loops. Okay, so if you're not comfortable with this blocked matrix multiplication coding style, you should pause the video now and draw the matrix diagrams to convince yourself. Just keep in mind that the loop ordering inside the block is K, I, J, and make sure you understand why you only fetch one element of A here and a line of B here. Okay. So when you're good, please move on to the next slide. Now we have all the code. We're going to synthesize the design and run it on board. We're going to set the data type to short, matrix size to 512, block size to 256, and it's going to take a couple hours to generate the bitstream. Let me share the execution time on F1. It's 5.5 seconds. Based on this number, we can compute the performance in gigaops using the method that we learned in the last lecture. It's a short operation, so we can't really say flops. We have to go with the gigaops. Okay. So there are two operations, one multiplication and one addition per iteration, and the complexity of the matrix multiplication is n cubed, and you divide by the execution time, and the performance turns out to be 0.049 gigaops. Now, this is a very bad number. We know that Vitis has automatically optimized the code, but it appears that it wasn't efficient enough. So let's check what the Vitis has done in the next slide. This is the synthesis log of the baseline code. You can find it in this path of your project directory. By the way, this part is the path for the hardware emulation. If you want to see the result for the bitstream result, you can just change it to hardware. Okay. And if you see the log, it'll tell you that the I loop was flattened, this one, and the J loop, this one, was pipelined. Flattened means that the I loop was combined with the J loop. This one was combined. So what Vitis did was apply some automatic optimization, but since it has a pipeline, the J loop, there wasn't enough parallelism. Remember, we decided to pipeline the second loop and unroll the innermost loop, right? So we can achieve a good trade-off between the resource consumption and the performance. But Vitis is not going to know that until you tell the tool which loop should be optimized in a certain way. So let's give those hints to the Vitis HLS. Our optimization strategy was to unroll the J loop and pipeline the I loops. So let's write it down, the unroll progma on the J loop and the pipeline progma on the I loop. Okay. Then ideally, we know that it'll perform m meg operations per cycle. But to make that possible, we also know that the internal memory needs to have enough ports to support loop unrolling. So let's partition the internal memory as well. In order to unroll this J loop, we need enough memory partition to supply the whole B line in parallel. Okay, and we also know that we need enough partition to read and write enough AB blocks in parallel. We don't need to fully partition the AB. We just need enough ports to parallelize the J loop. Okay, so for the B line, we partition the entire array. For the AB block, we just need to partition the dimension 2, this one, the one that corresponds to the J loop. Since all the J loops access the same I, you could array reshape the AB block if you want to do further optimization. Okay, makes sense? So that pretty much sums up the basic optimizations we need. We actually also need to pipeline the B fetch somewhere around here, and also pipeline the AB write somewhere over here as well. But I think you can fill that out on your own. All right. And before we see the effect of the explicit pragmas we have just added, I'll ask you one question. Some of you might have noticed that I have declared M, the block size, as a constant, whereas for N, the matrix size, I have declared it as a scalar variable in the function parameter list. Why did I do that? Well, to be exact, having M as a constant is required, whereas having N as a variable is recommended. Why is that? Why can't M change as well? Well, if you see where M is being used, it's being used in a loop that has been unrolled, right? You have to keep in mind that we are implementing this in FPGA, right? Not in a CPU. So FPGA is a hardware, and you typically cannot change the architecture of a hardware dynamically. The compiler has to know how many PEs and how many BRAMs it's going to utilize before it generates a bit string. Okay, so the unrolling factor and the partitioning factor, that the M that has to be fixed to a constant, and only then the Vitis compiler can generate a FPGA bitstream for you. Okay, makes sense? And why can N be a non-constant variable? N doesn't correspond to any of the hardware parameters. It's not like related to the unrolling factor or the array partitions. So we can make our design flexible enough to process any power of 2 squared matrices by making N into a variable. Okay. Now coming back, let's see how much the performance has improved after adding in the explicit pragmas for the pipelining and unrolling. The execution time has reduced down to 5.7 milliseconds, which corresponds to 47 gigaops. And if you compare that with the baseline implementation without any explicit pragmas, it's about 1,000 times better. So the lesson here is that the automatic optimization by the HLS compiler doesn't necessarily give you a good performance. Sometimes you have to intervene and give optimization hints to the HLS compiler. So now let's try to figure out if this performance is good enough or there's an opportunity for more. To do so, we can compare with the ideal performance. The ideal performance can be computed considering that we can do 256 mag operations per cycle. So 2 times, so multiply and add, times 256 mag unrolling factor times the F1 clock frequency about 250 megahertz. So this comes down to 128 gigaops, and this is the ideal performance. And 47 gigaops, this one is only about 36% of the ideal performance, which suggests that there is a room for further improvement. The reason for the low performance is the low effective DRAM bandwidth. Remember that the external memory access rate depends on the type of the top function argument, and we set the D type to a short type, so we're only going to copy one short type data per cycle from port A. So we cannot provide enough data to utilize all the MAC units. We're only utilizing like 16 bits out of a 512-bit XC bus. So we definitely need to apply some DRAM optimizations to increase the bandwidth, which we'll cover in the next class. Okay. So for the summary of this class, blocked matrix multiplication helps reduce the DRAM access by reusing the data stored in the internal memory. And while implementing matrix multiplication, we learned that we should choose a loop ordering that consumes a small internal memory and the one that improves the DRAM access bandwidth. And we found that the KIJ loop order is one configuration that has good characteristics considering these two. And instead of relying on the HLS automatic optimization, we could apply explicit pipelining, unrolling, and array partitioning programas for high performance. But still, we saw that we were short of the ideal performance, so we're going to apply some DRAM optimizations in the next class. So then I'll see you then.